Hello everyone and thanks for watching Edupedia World videos. So continuing with our topic, we are going to look at mathematical expressions for writing K equilibrium in this session. Okay? So basically we'll take up different reactions, different chemical equations and see how we can write the expression of K equilibriums for those reactions. Okay, and in various cases. Alright, so let's start with a simple example. Say you have HI, okay, you have HI going to H2 plus I2, right? And the balancing of this reaction, particular reaction, is given to you in this form. Okay, so now if you are asked to write the equilibrium expression, you can do it, okay, by writing the equilibrium expression in terms of either Kc or Kp. Let's assume for now that we are only writing the expression for Kc, which is basically molarity, okay, of products raised to their stoichiometric coefficient divided by molarity of reactants. So in this case the expression of Kc will be concentration of H2 into concentration of I2 divided by concentration of Hi whole square, okay, Hi square at equilibrium. All these concentrations are to be calculated at equilibrium. So to actually write the expression of Kc, I need to calculate these concentrations at equilibrium. So how do I do that? Okay, so in the exam or in the questions you will usually be given, okay, the amounts at t is equal to 0. Okay, so let's say I'm given that at t is equal to 0, the moles of reactant, here there is only one reactant, is A, and that of products is 0 and 0. Okay, so I can say that at any time t, okay, after any time t, alright, I am assuming here that 2x moles of Hi are consumed, okay, after time t, because we know that reactant is going to get consumed and products are going to get formed. Then I can say that if 2x moles of Hi are consumed, then x moles of H2 and x moles of I2 are going to be formed. Why is that? Okay, for this you have to go back and remember what we studied in mole concept. Alright, so there, okay, if you remember that, from there you will see that reactants are always consumed in their stoichiometric coefficient, okay, in proportion of their stoichiometric coefficient, and the products are always formed in proportion of their respective stoichiometric coefficient. Okay, once again, the reactants are always consumed in proportion of their stoichiometric coefficient. Alright, that means the stoichiometric coefficient of Hi here is 2, so it will be consumed, okay, in quantity of twice, okay, in twice the amount as the formation of H2 or I2, because their stoichiometric coefficients are 1 and 1 respectively. So consumption and formation of components in a chemical reaction depend on their stoichiometric coefficient in the balanced chemical equation. Okay, that is why the balancing is so important here while calculating Kc. Alright, so let's say that this time t refers to the time at equilibrium. So in that case these moles will become the moles of all your reactants and products present at equilibrium. So now I simply need to find the concentration. So how do we calculate molarity? Molarity is moles of solute divided by volume of solution. Let's say the container volume in which this reaction is taking place is V. Then this divided by V, this divided by V, and this divided by V. Okay, so Kc will simply be equal to molarity of I2, which is x by V, multiplied with molarity of H2, which is again x by V, divided by molarity of Hi whole square, which is, okay, which is A minus 2x by V whole square. So V will get cancelled and your final answer will be x square by A minus 2x whole square. Okay, so from here, if x is known to us, A will be given to you in the question. If x is also known to us, we can calculate the value of Kc. or the equilibrium constant for this particular reaction at this particular temperature T. Alright, or we can calculate the value of X if Kc is already given to us in the question. Okay, so what is the role of X here? So X, okay, X will give us the equilibrium moles or equilibrium concentrations of each of the component here. Okay, so that is the role of X over here. See, now let's say the same reaction, okay, the same reaction is given to you, but this time with a different balancing. Okay, so another examiner comes and he gives you the same question but with slight variation. In the variation is that the balancing done by this new examiner is different. Okay, now the question is still the same, that you have to calculate the value of Kc for this given reaction. If you have been given that at T is equal to 0, the moles of your reactant is A and that of your products are 0 and 0. So how do I do it now? So this time the expression of Kc becomes concentration of H2 raised to half concentration of I2 raised to half divided by concentration of Hi. Okay, so you see the equilibrium expression has obviously changed. Okay, and how do I write? Okay, how do I write these concentrations? Simply moles divided by volume. So how do I calculate the moles at equilibrium? So I can say that after any random time T, okay, if A was the initial moles of Hi, then A minus X can be said to be the moles left, okay, of Hi after time T, where X is the moles of Hi consumed after time T. So if X is the amount of Hi consumed, then X by 2 and X by 2 are the amounts of H2 and I2 formed. Okay, once again, why? Because 1 is the stoichiometric coefficient of Hi and half is the stoichiometric coefficient of H2 and I2 respectively. So the consumption and formation are always in proportion to stoichiometric coefficient. Okay, so if this time T represents the time at equilibrium, then these moles represent the moles at equilibrium, and when I divide them by volume, these will represent concentrations or molarities at equilibrium. So Kc will now be H2 to the power half, that means X by 2V raised to half into I2 concentration raised to half, which is again X by 2V raised to half divided by concentration of Hi. Okay, so divided by A minus X by V, right? This is my new Kc now. Okay, the X in the two cases is different. Okay, in this latter case, okay, in this latter case, X is the moles of Hi consumed by the time equilibrium was attained in our container. In the first case, X is not that. Okay, in the first case, 2X is the moles of Hi consumed by the time equilibrium was reached. Instead, X is the moles of H2 or I2 formed by the time equilibrium was achieved. Okay, so the values of X here in the both the cases are different. The definition of X itself is different, and for our purposes even the reaction can be said to be different because the stoichiometric coefficients are different. Okay, if you see, the second reaction is simply obtained by multiplying the first reaction with half. That means the equilibrium constant for the second reaction will simply be equal to the equilibrium constant of first reaction raised to the power of half. Alright, let's take another example. Okay, a different reaction this time. Let's take the formation of ammonia. Okay, a reaction where two reactants are simultaneously involved to form one single product. Okay, and the balancing or the stoichiometric coefficient of each one of them is different. Alright, this is how you can balance the reaction. So stoichiometric coefficient of nitrogen is 1, that of hydrogen is 3, and that of ammonia is 2. Alright, so once again our goal is to write the value of Kc for this reaction. So in this case, Kc will simply be equal to concentration or molarity of ammonia whole square divided by concentration of N2 and concentration of H2 cube. Alright, so I simply need to find the concentrations at equilibrium. Let's say at T is equal to 0, you have been given A moles of nitrogen with you and B moles of H2 with you and 0 moles of product. Alright, so this time you have two different reactants and whose initial quantities are also different. Okay, so how do you write the expression at equilibrium? So at equilibrium, I can say that the moles have now become, okay, A minus X, where X I have assumed to be the moles of N2 consumed by the time equilibrium is achieved in the container. Okay, so you can see from the stoichiometry, 1 mole of nitrogen requires 3 moles of hydrogen. That means X moles of nitrogen will require 3x moles of hydrogen. Okay, that is, once again, moles are consumed in proportion or in the ratio of their stoichiometric coefficients. So if X is the moles of N2, then 3x will be the moles of H2 consumed. Similarly, 1 mole of nitrogen here forms 2 moles of ammonia. That means X moles consumed of nitrogen will form 2x moles of ammonia. Okay, so once again, if these are divided by volume, you can simply write the expression for Kc as 2x by V whole square divided by A minus X by V into B minus 3x by V cube. Alright, so it's as simple as that. Let's say the same question is given to you, everything is same, even the balancing is same, but the student solving the question is different. Let's say another student comes in and he says that instead of defining or writing the expression in terms of X, where X is the moles of nitrogen consumed at equilibrium, the student says, I want to write the same expression in terms of moles of hydrogen consumed. Okay, so the same question can also be solved. Alright, what is the question? The question or the goal is to write the equilibrium expression, okay, for this reaction and to find the value of Kc. Okay, so the same answer Kc will have the same value with both the methods. The second method involves, okay, a student who writes the expression at equilibrium in terms of moles of hydrogen consumed and not of nitrogen. Okay, so he says that at equilibrium, if, okay, at T is equal to T equilibrium, if Y moles of hydrogen is consumed, then how much N2 will be formed, or sorry, how much N2 will be consumed? It will be A minus Y by 3. Okay, so here Y by 3 is the moles of N2 consumed and A minus Y by 3 is the moles of N2 still left unreacted in our container. Is this clear? Okay, see, basically once again, in the ratio of stoichiometric coefficient, so 3 moles of H2 requires only 1 mole of N2. Okay, that is, the amount of N2 required is 1/3 of the amount of H2. So Y moles of H2 consumed will require only Y by 3 moles of N2 for reaction to take place. So Y by 3 is the amount of N2 consumed, nitrogen consumed, and the amount of nitrogen still left unreacted is A minus Y by 3. Similarly, the amount of hydrogen still left unreacted in the container is B minus Y. Alright, now 3 moles of hydrogen forms 2 moles of ammonia. Alright, so Y moles of hydrogen consumed will form 2 by 3 Y moles of ammonia. Okay, so that is, alright, if 3 moles of hydrogen forms 2 moles, then 1 mole of hydrogen will form 2 by 3 moles of ammonia. Okay, so Y mole of hydrogen will form 2 by 3 Y mole of ammonia. Alright, so this is how you can write the expression in terms of consumption of hydrogen instead of nitrogen. Okay, the final expression will look different. Okay, this will become 2 by 3y divided by volume square, okay, into 1 by a minus y by 3 divided by volume, okay, into b minus y by v whole cube. Okay, so the expression of Kc in both the cases might look different. Okay, all right, but it doesn't matter. Okay, the final answer of Kc for using both the methods will still be the same. Okay, in fact, another student might come and he might decide to write the expression in terms of moles of ammonia formed. Okay, so in this one we wrote the expression of Kc in terms of moles of nitrogen consumed. Here we wrote the expression in terms of moles of hydrogen consumed. So another student might come up and he might want to write the expression in terms of moles of ammonia formed. Okay, so you can still do that. All right, so let's say you have the same question, right? N2 plus 3H2 gives twice of ammonia. Alright, so here again at T is equal to 0, A moles and B moles of H2 are given to me and 0 moles of ammonia are given. Okay, now at equilibrium, okay, the student says I want to write the expression in terms of moles of ammonia formed. Let's say he assumes that moles of ammonia formed is X, or even better, moles of ammonia formed at equilibrium, okay, is assumed to be Q. Alright, so the students assume moles of ammonia formed at equilibrium to be Q. So this means the moles of nitrogen consumed will be A minus Q by 2. Is this clear? Sorry, Q by 2 is the moles of nitrogen consumed at equilibrium and A minus Q by 2 is the moles of nitrogen left at equilibrium. Why is that? See here, 2 moles of ammonia are formed by 1 mole of nitrogen. Okay, that means consumption of nitrogen is half the value of the formation of ammonia. Okay, so that is, if Q amount of ammonia is formed, then half of Q is the amount of nitrogen consumed to form that much ammonia. Alright, similarly, if you look at hydrogen, B moles of hydrogen were present with you. Out of these B moles, how much hydrogen is consumed? So it will simply be 3 by 2Q. Alright, that is, once again, the consumption and formations are in the ratio of their stoichiometric coefficient. So 2 moles of ammonia consumes 3 moles of hydrogen. That means 1 mole of ammonia will consume 3 by 2 moles of hydrogen. That means Q mole of ammonia will consume 3 by 2Q moles of hydrogen. Alright, so you should just try and get a feel of this. Okay, all these expressions, the different ways of writing the same reaction, okay, and finding out the expression of Kc in each of the cases. So here it will become Q by V whole square. Here once again, V is the volume of the container in which reaction is taking place. Why are we dividing everything by V? Because the expression of Kc involves concentration or molarity, not moles. So we have to convert moles to molarity before writing the expression of Kc, and molarity is moles divided by volume. That is why we are dividing everything by volume V of our container, which should be given to us in the question, in the example, for us to calculate the actual value of Kc. Alright, so in the next few sessions we'll solve some questions based on the theory that we just studied. Okay, the theory is basically how to write mathematical expressions for K equilibrium. So in this particular session we only looked at writing mathematical expression of Kc, okay, which is in terms of molarity. In another session we'll look at how to write the mathematical expression for Kp, okay, which is in terms of partial pressures, right? So there we'll be able to look into all of this in greater detail. Okay, also remember the calculation part, okay, the calculation of units as well, because while writing the final answer for Kc you will also have to write the unit with the value. So unit is moles per liter raised to power delta n, okay, where delta n is stoichiometric coefficient of product minus stoichiometric coefficients of reactants, okay, so which we have already covered before. Alright, so until next time, and once again thanks for watching Edupedia World videos.